In our strange world of countless climatic shifts, there is a period in Earth's history that continues to captivate researchers. 12,900 years ago, a time when mammoths and saber-cats roamed the lands and humanity was on the brink of a new era, something changed. Just as life seemed to be flourishing, a remarkable event unfolded, transforming the world as we know it. In a period of decades, temperatures plummeted, icy winds swept across continents, and vast sheets of ice once again advanced. This period lasted for over 1,000 years before subsiding as quickly as it arrived. But what caused this sudden and drastic change? How did it affect human populations, and was it even that remarkable after all? Today we will thoroughly discuss the Younger Dryas, leaving no stone left unturned. It is an extremely complicated topic, and as always, my sources can be found in the description. The Younger Dryas period has been known of for a relatively long time. It was easily distinguishable in paleobotanical and lithostratigraphic studies of Scandinavian sites. The name Younger Dryas refers to the wildflower Dryas octopetala, a plant which thrives in alpine and tundra conditions. Its presence in sediment layers indicates a typically colder, glacial climate. The younger part of the name refers to the fact that it was not the only climatic fluctuation during this period. It is called the Younger Dryas because it is one of 3 colder periods called stadials which came after the last glacial maximum. The Younger Dryas was indeed more abrupt than the older or oldest Dryas, though not unprecedented. It essentially reversed the warming of the Earth back to glacial conditions. But keep in mind, although it was cold, it was not colder than a few thousand years before when the Earth was in the last glacial maximum. Analysis of Greenland ice cores provides accurate estimates for the beginning and the end of the Younger Dryas. It is estimated that the period started around 12,900 years ago and ended around 11,550 years ago, meaning that the period lasted between 1150 and 1300 years. Though the actual timing of the event introduces us to our first mystery. The Younger Dryas did not start synchronously across the world, and even varied across the North Atlantic region, the region which was affected the most. Evidence suggests that cooling occurred as early as 12,900 to 13,100 calibrated years ago along the latitude 56 to 54 degrees north, in at least northern Europe. Cooling further north between 60 to 58 degrees occurred significantly later between 12,600 and 12,750 years before present. Cooling did not reach northern regions of Europe for hundreds of years. When looking at regions outside of the North Atlantic, the onset of the Younger Dryas becomes even more confusing. Analysis of lake sediments from Japan and other records from Asia report a substantial delay in the start of the onset of the Younger Dryas. The temperature in Japan only appeared to decline around 12,300 years ago. This is of course around 500 to 600 years later than much of the northern hemisphere. Data from Chinese sediments also confirm that the Younger Dryas of East Asia lags behind the North Atlantic cooling by at least 200 to 300 years. In the Philippines, analysis of stalagmites found that the Younger Dryas conditions did not reach the region for nearly 600 years after they appeared in northern Europe. And even these conditions appear to have been quite mild. This is another interesting fact about the Younger Dryas. It by no means affected the world equally. Regions in the northern hemisphere, especially around the Atlantic, were affected the most. Even though the Younger Dryas did not occur at the same time all over the world, in much of Europe the conditions changed dramatically in only a few decades. In some areas, the onset of the far colder conditions may have happened in less than a decade. People living in Europe would have certainly noticed the colder and much drier conditions. In Greenland, temperatures drop between 4 to 10 degrees Celsius or 7 to 18 degrees Fahrenheit. In the British Isles, beetle fossils indicate that the annual temperature dropped to -5 degrees Celsius or -23 degrees Fahrenheit. Though the winters would have been cold, multiple studies confirm that localities in Europe experienced quite short but warm summers. An extensive study on the vegetation of central Iberia found that the effects of the Younger Dryas were actually quite mitigated, at least early on. From 12.6 to 12,000 years ago, the conditions were dry and quite warm, while from 12 to 11.7 thousand years ago, they were wetter and cooler. The Middle East appears to have been affected much less, though drier and colder conditions did occur even starting before the Younger Dryas and lasting after it concluded in other places. North America in particular was the other region most heavily affected by the frigid conditions. This is not surprising considering its proximity to the Atlantic, which appears to have been a large factor in the cooling. Though there is evidence of cooling that predates the Younger Dryas by hundreds of years, particularly in the east, which of course is in direct proximity to the Atlantic. The rest of North America did begin to cool around 12,900 years ago, though some areas were affected much less than others. In the northeast United States, temperatures dropped by around 7.5 degrees Celsius, causing frigid winters and cool summers with little rainfall. The change in conditions was disastrous to forests, causing the spread of tundra. In the northern interior, the massive Laurentide ice sheet, which had been decreasing in size for thousands of years, once again advanced. The Great Plains in general became much colder with tundra-like conditions except for areas closer to the Gulf of Mexico. The Rocky Mountains seem to have been isolated from much of the cold. West of the Rockies, conditions became 2 to 3 degrees Celsius colder and saw increased precipitation and the expanse of glaciers. The Gulf of Mexico appears to have been slightly colder while the Caribbean experienced warming. When we move to the southern hemisphere, we see a much different effect of the Younger Dryas. Many regions appear to have been more or less unaffected, and many even experienced slight warming. Venezuela experienced cooling, though much of South America seems to have gotten warmer. Glaciers in both Peru and Bolivia retreated. Africa seems to have been affected in a variety of complicated ways. North Africa, which at the time had a very lush Sahara, does not seem to have been affected much. Western tropical Africa slightly warmed while the east slightly cooled. Various regions of Africa do appear to have become more arid during this period, though significant cooling appears to have been absent. Asia was also affected in a variety of complex ways. Oceania appears to have hardly been affected by the climatic event. There is even evidence that Australia became warmer and wetter during the period. Since the Younger Dryas was a return to glacial conditions for much of the world, glaciers expanded. This caused the sea level to lower at a rate of about 2 to 4 centimeters per year until the end of the period. From the start to the end of the period, sea levels decreased between 20 to 40 meters. This is a significant amount, though keep in mind, the oceans are currently rising at about this same rate and it is hardly perceptible to most. Overall, the Younger Dryas was a strange period that temporarily put the world back into glacial conditions during a time when the Earth was steadily warming. The frigid and dry conditions undoubtedly drastically affected the human and animal populations of the period. But before we talk about how our populations reacted, we must first discuss the cause of such a peculiar event. The cause of the Younger Dryas has been quite a hot topic, especially in recent years. Multiple hypotheses have been proposed with various degrees of success in explaining the phenomenon that was the Younger Dryas. Perhaps one of the most essential things we must first understand about the Younger Dryas is that it lasted for over 1,000 years. Any complete explanation of the period must have caused sustained cooling and not just a momentary climatic change. And this brings us perhaps to the most likely explanation of the event. The sustained cooling of the northern hemisphere and the warming of the southern hemisphere suggests that the event may have been caused by a change in the ocean's currents. More specifically, the shutdown or reduction of the North Atlantic conveyor. The Atlantic Meridional Overturning Circulation, or AMOC for short, is part of a global circulation of currents which brings warm, salty water to the North Atlantic and carries cold water southward into deep waters. Two things to keep in mind about this circulation is that it is based not only on temperature but also the salinity of the water. This process is well studied in the modern era, though many aspects about how it functions remains enigmatic. One thing that researchers have identified is that it is anything but stable. Not only is there evidence that it was heavily varied in prehistory, but even in the modern era. Evidence suggests that the AMOC is weaker than it was prior to the Industrial Revolution. Many have hypothesized that the Younger Dryas may have been directly caused by the influx of cold fresh water into the Atlantic Ocean. First, we should talk about what was happening prior to the Younger Dryas. The world was gradually moving from a glacial period into an interglacial period. This of course means that glaciers were melting and the world was warming. Deglaciation caused the sea levels to rise, but also the formation of massive meltwater lakes all over the northern hemisphere. One of these lakes, Lake Agassiz, was absolutely massive. The lake covered as much as 440,000 square kilometers or 170,000 square miles. It has long been thought that this body of water may have caused a sudden and perhaps sustained influx of fresh cold water into the Atlantic, which would have undoubtedly affected the AMOC. Further research has identified a pathway along the Mackenzie River that would have brought the glacial melt all the way to the Arctic and thus the Atlantic. You may say, but the Arctic is already cold. Why would this change anything? But you must remember that this was fresh water. Fresh water is much less dense than salt water. The influx of massive quantities of this less dense water into the Atlantic would have disrupted the delicate mechanics of the AMOC. Water may have also flowed eastward straight into the Atlantic, though this has yet to be proven. Though a singular flood of fresh water into the Arctic and Atlantic would have not caused sustained cooling for over 1,000 years. It is estimated that the AMOC would have recovered in less than 100 years from such an event. Instead, a large sustained flow must have been present to cause these conditions for most, if not all, of the Younger Dryas period. Though all of this may sound hypothetical, much of our evidence suggests that this was the case. Changes in microscopic life within the ocean suggest a significant change in ocean currents. Not only do we have evidence of where the water entered the ocean, but modern studies on the AMOC suggest that cold fresh water would have certainly been capable of causing prolonged cooling. Other studies suggest that a major ocean flushing event may have been an important component in the reduction of the AMOC. Right before the onset of the Younger Dryas, several CO2 records show a sharp increase and a subsequent decrease. The saltier ocean of the time may have accumulated geothermal heat and built up potential energy. It may have been released rapidly, perhaps catastrophically affecting the AMOC. Evidence suggests that this event occurred and it may have been caused by an influx of meltwater, though this remains enigmatic. Evidence also suggests that these events may have occurred at multiple points in the past. Even more compelling, our evidence suggests that the Younger Dryas is merely one of 25 similar events that occurred over the past 120,000 years. Similar events almost appearing identical in ice core graphs called Daskar-Oshker events are thought to have been triggered by meltwater and variability of the carbon cycle. A 2020 paper proved that the Younger Dryas is statistically consistent with the other DO events. With this evidence at hand, the Younger Dryas does not appear unusual whatsoever. It may simply be a small part in the larger climatic variation that has regularly occurred on Earth since the start of the Ice Age 2.5 million years ago. Though it may sound like we have the Younger Dryas all figured out, we must not forget that we are talking about climate. Climate is endlessly complicated and many other factors must be considered. Various researchers have suggested that a reduction of the AMOC would not be enough to cause such a sudden and prolonged cold period. Variations in solar radiation and complicated atmospheric circulations could have played just as much a part in the cooling. These explanations are most commonly cited in the scientific community as the cause of the Younger Dryas. However, there is one that has gained a lot of traffic in pop culture. Of course, I am talking about the elephant in the room, the Younger Dryas Impact Hypothesis, or YDIH for short. First, I must preface the discussion of this topic by saying that it is neither an outlandish hypothesis nor anything close to a proven fact. There is certainly some evidence supporting aspects of the hypothesis, though most experts reject the hypothesis based on a lack of repeatable, testable evidence. The Younger Dryas Impact Hypothesis posits that fragments of a large extraterrestrial object airburst and struck various areas of the world around 12,900 years ago. It hypothesizes that the impact may have caused widespread fires, an impact winter, the Younger Dryas period, and the extinction of various megafaunal species. Evidence comes in the form of various hypothesized impact markers and layers dated to the period, and also black mats widely distributed dating to this time. Approximately 2/3 of the sites dating to the onset of the Younger Dryas contain black mats. These mats are a black, organic-rich layer found across multiple continents. They are considered by proponents of the impact hypothesis as evidence of widespread fires that occurred after an impact. Mats such as these have certainly been found in some cases to represent volcanic eruptions and extraterrestrial impacts. However, for this to be the case, clear evidence of synchronous deposition must be found, or in other words, it must be clear that they were all deposited at the same time. A 2020 study found that the C14 from the Younger Dryas boundary are inconsistent with synchronous deposition. The authors concluded that the synchronous deposition of the Younger Dryas boundary is extremely unlikely. Furthermore, black mats are known throughout many time periods and appear to simply be characteristic of wetland environments. Evidence from both the southwest United States and Chile show high levels of iridium and magnetic sediments in various sites between 6,000 to 40,000 years ago. These supposed impact markers are found in these mats regardless of age or location. Some of these layers do appear to be evidence of wildfires, but not necessarily impacts. A 2009 study suggested that wildfires did occur during the Younger Dryas boundary, though they were a natural consequence of the rapid climate change of the period. Another study found no evidence that these hypothesized fires were impact-induced. The existence of these layers at the Younger Dryas boundary is only natural considering the Younger Dryas featured a dramatic change in precipitation and moisture in general. Considering these mats are not deposited at the same time, they cannot be contributed to one event, such as a comet strike. Besides easily visible evidence, researchers have also looked into small signatures and layers dating to the Younger Dryas boundary. Nanodiamonds are one of the most important forms of evidence that have been used to support the impact hypothesis since its inception in 2007. Though nanodiamonds can be found in sediment due to wildfires, volcanism, or even occasional meteoric debris. A 2014 study about nanodiamonds based on 49 sediment samples from a range of dates did indeed find a spike during the Younger Dryas. However, it also found similar sized spike in the Holocene around 3,000 years ago and in modern topsoil. Of course, a massive climate-changing asteroid has not impacted us recently, and neither did it happen 3,000 years ago. Another analysis of a similar Younger Dryas boundary layer from Belgium displayed carbon crystalline structures such as nanodiamonds. Though the authors came to the conclusion that they did not show unique evidence for an extraterrestrial impact. Platinum is another source of evidence which is often used to support impacts in general, though other explanations such as volcanism can explain its presence. A 2019 study found evidence in South Africa of a spike of platinum in layers dating right before the Younger Dryas. The site is now one of around 25 sites in Europe, Asia, and North America which have reported platinum. The authors of this paper suggest that the impact hypothesis could be a possible explanation, though critics were quick to point out that volcanic activity could be responsible. We will talk about this later. Magnetic microspheres are another main form of evidence used to support the impact hypothesis. First of all, there is no consensus about the origin of these microspheres or the significance of their concentration. Various studies have found evidence of spikes in Younger Dryas boundary layers, but have often been heavily criticized for not being reproducible. An important 2016 study conducted a blind test of two different labs to identify magnetic microspheres from layers before, during, and above the Younger Dryas boundary. Both labs found very low or non-existent levels on either side of the boundary. One exception from 11,500 years ago had a spike in microspheres, though keep in mind the Younger Dryas ended around 50 years before this date. And regardless, if an impact was responsible, we would find this evidence at its onset, not its termination. The study also found that reproducing this data, even among themselves, was problematic and noted that the purported impact proxies are not unique to the Younger Dryas boundary. Perhaps an obvious explanation for the appearance of impact markers in various places around the world during the Younger Dryas is that there were impacts. But the Earth is constantly bombarded by asteroids of various sizes, and these signs are found in many layers where there wasn't a climatic shift. One article pointed out that many of the impact markers pointed out by the original impact hypothesis study are not even consistent with a single impactor, but rather from a diverse array of micrometeorites. This is one of the problems for much of the evidence of impact. If you are looking for impact markers in the soil, you may find them, but correlating an impact with a larger scale climatic change is much harder to do. If there was a massive crater dating directly to the start of the period, a strong case could be made. There is a crater in Greenland which was thought that could have dated to this time, but it was later dated to around 58 million years ago. Though in regards to the impact hypothesis, there may not even be one massive crater if the object fragmented across much of the world and mainly impacted glaciers. This poses a logical problem for the hypothesis. Embedded in it is a mechanism by which the evidence of the impact was destroyed or not preserved. If the only evidence found of an impact is spread faintly throughout the world resembling micrometeorite debris, then where is the evidence that a climatic changing impact even occurred? Furthermore, the best evidence put forth to support an impact suggests an iron meteorite instead of a comet. Such a dense object of the size being proposed would still leave a crater even if it impacted the Laurentide ice sheet. And if it airburst, it would likely not even distribute evidence as far as Africa or Asia. Critics have stated that the Earth certainly does not need an extraterrestrial impact to have caused the weakened AMOC in the first place. Not only is the evidence asynchronous and inconsistent, but the Younger Dryas appears to be simply a part of a repeating cycle of climatic changes and only appears significant because it happened to be the last major change before the start of the Holocene. We currently do not have enough evidence to sufficiently support a large impact 12,900 years ago, and we certainly do not have enough evidence to suggest it directly caused the Younger Dryas. Though I still advocate for not immediate denial of this possibility. There certainly could be definitive proof out there, but our evidence as of 2023 supports the conventional explanation of a number of factors, including a weakened AMOC. People often accuse mainstream academia for not being accepting of new ideas or controversial ideas such as the impact hypothesis. But if this were true, why are there dozens of papers advocating for this? Even papers that are not necessarily for the impact hypothesis advocate for its further investigation even in the late 2000s. Despite what some may tell you, science is not characterized by old dogmatics suppressing new discoveries. At the end of the video, I will further address pseudoscientific claims, though we must first discuss another possible cause of the cooling period: volcanism. Volcanic eruptions, although quite hot, can actually cause the Earth to cool quite considerably. A 2020 study found that an impactor could not reproduce the observed chemical patterns found in the sediment from a site in Texas and appeared to be more consistent with that of an eruption. The paper also importantly mentions that other previously found impact markers such as wildfire products and nanodiamonds could have certainly originated in large-scale volcanic eruptions. A 2021 study on the Lacquer Sea eruption proved that it happened slightly before the onset of the Younger Dryas. Researchers believe that it certainly could have caused cooling in the northern hemisphere and be responsible for some but not all impact markers. This eruption, alongside other factors such as a weakened AMOC, could have been primarily responsible for the cold period, while further research would need to be done to prove this. We have covered in significant detail what may have caused the Younger Dryas, but now we must discuss how it actually affected the human populations of the time. For many, the onset of the Younger Dryas meant a return to frigid glacial conditions. This was certainly the case for those living in Europe and much of North America. Northern Europe appears to have been hit the hardest by climatic changes. The tree line lowered, tundra expanded, and animal populations contracted. The British Isles, which were connected to the mainland at this time, were hit particularly hard. Temperatures in January were between 10 to 30 degrees Celsius cooler than today. Our evidence of human habitation decreases, and the practice of burial seems to have stopped entirely. At some times, the area which is now the British Isles may have been mostly uninhabited. Northern Europe was very frigid during this time period, and Scandinavia was almost entirely covered by glaciers, as it more or less had been for thousands of years. Most of Europe would have been generally drier due to the colder conditions year-round. This also appears to have been the case for areas of Western Asia and North Africa. As mentioned earlier, a study found that localities throughout Europe would have actually had quite warm summers, although they would have been short. Populations in Iberia do not necessarily seem to have decreased, though it appears that the Younger Dryas period did stagnate growth. A similar story may have played out throughout much of Europe, though population studies currently provide no clear answers. A decline or stagnation is almost certain. I find it extremely important to mention that a population decrease associated with colder conditions is in no way out of the normal. North America is the other region which appears to have been affected the most by the onset of the Younger Dryas. It is associated with the decline of the Clovis culture and the extinction of many megafaunal species such as mammoths, saber-toothed cats, dire wolves, and many more. Though evidence suggests that many of these species experienced a population crash 1,000 years before the onset of the Younger Dryas. The cause for this is unknown, though it now appears to not be as directly correlated to climate as once thought. One study determined that Paleo-Indian populations at the start of the Younger Dryas did not experience an initial population decline. Another study found that their populations did decline significantly in the following centuries after the onset of the Younger Dryas before swiftly rebounding and expanding. Right at about 12,900 years ago, stone quarries appear to have been abandoned, while the number of projectile points also declined in some areas by around 50%. It is unknown how population numbers were affected because stone use is not directly correlated, especially considering a clear cultural reorganization that was occurring during this time. Depending on the region, these populations appear to not only have rebounded but expanded in as little as 200 years. Interestingly, the Clovis tool-making tradition seems to have directly evolved into the Folsom culture during this period, at least in some places. The Folsom culture appeared right at the start of the Younger Dryas 12,900 years ago. Their sites appear simultaneously with Clovis sites, indicating that both traditions were still practiced, though eventually through the Younger Dryas the Folsom tradition came to prominence. Despite the colder conditions, the Folsom culture was able to thrive, experiencing a population and geographic expansion. The Folsom culture is characterized by the creation of very sophisticated stone technology and a specialization towards bison hunting. This specialization appears to have been a consequence of the extinction of much of the North American megafauna. With most of the giants faded into oblivion, bison for whatever reason survived, and the Folsom culture took advantage of this. After all of these years, we still do not know why megafaunal populations experienced this crash. Some evidence suggests that the human hunters were really that deadly, while other evidence suggests that climate played a large role. Considering their population began to collapse 1,000 years before the Younger Dryas, an impact event could not solely explain the decline. Regardless of what caused the decline, we know that it happened in both North and South America. Human populations from South America also appear to have been more or less unaffected by the climatic changes, while many species of megafauna were lost. As stated earlier, the temperature and precipitation hardly appears to have changed during the Younger Dryas in most of South America. Despite this, the megafauna died out just the same, perhaps suggesting that overhunting played a larger role than climate, at least in this area. Moving across the Pacific, archaeological records from Japan show little change from before and after the onset of the Younger Dryas. Populations stayed relatively the same, and ceramic pottery technology was consistently used. Though after the Younger Dryas period ended, the quality of their pottery did increase significantly. North Asia in general appears to have cooled, but not significantly, and populations do not seem to have been affected significantly either. The same can be said about Eastern and Southern Asia in general. We do not have evidence that these areas got colder or necessarily drier. Australia, in fact, even warmed up a bit. The populations living in these areas show no decline and would have likely not noticed the change. The megafauna in these areas had already gone extinct thousands of years before, especially in Australia. this being evidence often cited by proponents of the overhunting hypothesis that it was humans that made the megafauna go extinct. Regardless, it cannot be overlooked that the younger Dryas did not have nearly the same effect on the southern hemisphere and Asia in particular. Finally, circling back to Western Asia, we find perhaps the most important effect of the younger Dryas. The less abundant times may have directly caused the Neolithic Revolution. Prior to the younger Dryas, Natufian people of these regions were exploiting their environments so effectively that they could live in sedentary villages. This is a big contrast from almost every other population of the time, which has had to constantly move to more abundant areas. They were able to do this by exploiting many animals and plants of their environment, importantly grasses. The region began to become colder and drier before the onset of the younger Dryas and sustained this trend throughout the subsequent period. The drier conditions caused the spread of grasslands and consequently led to a shift in their diet. The reliance on grasses and sedentary life is thought to have been an important step toward full-scale agriculture. A discussion of the younger Dryas would not be complete without covering the events of its ending. The end of the younger Dryas is very significant because it also marks the final end of the last glacial period. Oxygen isotopes suggest that the ending of the younger Dryas took between 40 to 50 years, starting 11,550 years ago. Some areas even display evidence that significant warming occurred much faster than this. Other areas, particularly in Asia, show that the end of the younger Dryas occurred later. With the end of the younger Dryas and subsequently the last glacial period, the glaciers of course significantly diminished in size. All of this fresh water drained into the oceans, causing the sea level to rise. This rise is known as meltwater pulse 1b. Over a period of about 160 years, the sea level rose by around 7.5 meters or 24 feet. That is about 4.6 centimeters or 1.8 inches per year. That is not a lot, but still significant over a long time span. To put this in perspective, the sea level is rising about 0.34 centimeters a year or 0.13 inches, meaning that during these 160 years, it was rising about 14 times faster than it is today. It is debatable if this amount would even be perceptible to coastal inhabitants and certainly not to people living inland. This rise in sea level occurred during the last 2 centuries of the younger Dryas, and if you remember from earlier in the video, during the rest of the younger Dryas, the sea level was actually decreasing by about 0.34 centimeters a year. Nowhere before, during, or after the younger Dryas was there a global flood or even evidence that the sea level rose particularly quickly. There were indeed massive glacial floods in some very specific areas, such as the channeled scablands of southeastern Washington. An interesting thing to note about the scablands is that at least 40 cataclysmic floods have occurred there, 39 of them not having anything to do with the younger Dryas. Besides globally rising sea levels, many living around the world would have hardly noticed the onset or the end of the younger Dryas. As mentioned previously, human populations in most of the southern hemisphere were hardly affected, and even animal populations were affected in a number of ways not necessarily correlated with the younger Dryas. The southern hemisphere happens to be where most people would have been living 11,500 years ago. Coastal shelters may have moved, but keep in mind, the vast majority of humans at this time belonged to extremely nomadic groups. It would have not been any problem at all to move a camp from an inch of sea level rise over the span of an entire year. Therefore, no, the younger Dryas was not an apocalypse in any way, shape, or form for our species. Populations living in North America and Western Europe certainly had to adapt to the new colder conditions, and the extinction of the megafauna did cause culture to change and an initial population decline, as we saw with the Clovis-Folsom transition. Though even this fast change in lifestyle for Paleo-Indians subsequently resulted in a population expanse rather than a decline within the period. Northern Europe certainly did witness a population decline, though not apocalyptically. With our knowledge that the younger Dryas was one of many seemingly identical climatic changes, calling it a cataclysm should be seen as exaggerated. The megafaunal collapse of North America may be seen as a catastrophe, but again, it cannot solely be linked to the younger Dryas, as their populations appear to have already been declining. More importantly, with the end of the Younger Dryas, we see the first emergence of agricultural and megalithic societies in the Near and Middle East. This shift in lifestyle was gradual, but put us on a trend of progression throughout the Holocene.